today I want to talk about this project that has been taking most of my time for the past 2 years, and which has been developed by a number of contributors and led by Ron, who is the PI of this project. This talk will be about NCI imaging data commons, but I want to kind of set the stage before talking about IDC, talking about why we care about the data, what is different about cancer imaging data, and what is it, data commons? Because I think it's still quite a new concept, and in many ways it still is remains to be proven what is the utility of data commons and how to properly implement data commons for this community. Then I will talk about the status of imaging data commons, its main features, and I hope there will be time for a quick demonstration of some of the capabilities we are currently providing, because ultimately success of this project is up to users like you who will hopefully find it useful, give us feedback what you want to see in this project and how it can help your research. So let me start with the data. And for me, I was, as Ron mentioned, data sharing and thinking about how to do it properly has been a significant focus of my work in several projects. But perhaps the striking moment for me was at the World Medical Innovation Forum in 2018, when the CEO of NVIDIA, Jensen Huang, was speaking. And he put it very clearly, saying that your source code is your data. In the going forward, it is not going to be as important what your algorithm is, what kind of network you are training, but what kind of data you use to train that algorithm. So thinking about how to collect the data, what data to collect, what should accompany the data that you're collecting, how to annotate it, how to maintain this data is absolutely critical. And in the recent years, with the emergence of AI, this topic has become very important and well recognized. However, if you look back about 10 years back, it was not so obvious at those days. And one defining moment for AI and image recognition research was the work on the defining the ImageNet database. Back in 2006, sorry, the focus was mostly on how to come up with a better algorithm. And the thought process was that if we have a better algorithm, we can solve the more complicated problem. Fei Li, at that time, she was a faculty at Carnegie Mellon, I believe, decided that what about looking at this problem a bit differently? What if we try to collect comprehensive data to train our algorithm? And as it turned out, that this was a very interesting idea, which was not recognized at the time by either funders or publishers. She was presenting this research in an obscure poster at a conference at the time, and failed to secure any funding to complete this work. But she persisted, and in the end, she led the initiative that collected this very comprehensive data set that really led the revolution of AI. And if you look at what ImageNet is, it's millions and millions of images that are very carefully annotated with the locations of the objects in the images, and also annotated with the sort of an ontology that tells you what is that thing annotated by this bounding box. Once this data set was curated, and once researchers started using this data set for training their networks, performance of the algorithms really improved dramatically. And at this point, the recognition of objects in visual recognition is considered by many a solved problem, at least the way it was defined at the time when this challenge was started. Of course, you all know that in cancer imaging, medical images, we do not have anything like ImageNet. And there are many good reasons why this is the case. Of course, the main reason, which often is a main stumbling block, is the privacy. We are not sharing images of cats and dogs. These are real people with their lives, with their health conditions, and it's very important to respect their privacy. At the same time, the fear for inadvertently leaking the patient information often prevented institutions to share the data, and institutions often feel ownership of the data for other reasons, and perhaps sometimes those concerns are not always well justified, because there are techniques to deal with the privacy of the information in the images. Of course, also the data we deal with in cancer imaging, medical images, has a lot more variability than the tasks solved by the ImageNet challenge. There are all those sources of variability that you are all familiar with. In addition to that, to do meaningful analysis of images, we also need interpretation and annotations of those images that are created by experts that have their own variability, that can have their own biases, and often require multiple annotators to come up with meaningful reference data. And finally, we can't share just the images, because the meaningful analysis of imaging is not possible without the clinical data, demographics, and various other types of data which is collected as part of clinical care and patient management. So here is one data set which I think is one of the most prominent examples of successful large-scale database that was collected and shared. This is a national lung screening trial which took place in early 2000. And as a result of this trial, for more than 26,000 of patients, the CT imaging data accompanied by very detailed clinical data, survival and prognosis of those patients was shared and is now available to cancer researchers. So it's one example, but it's one of the growing number of examples where data collected in clinical trials is being shared with the community. In addition to sharing data that comes from large studies and large clinical trials, individual researchers also are starting to share data more and more often. It was actually found that those researchers that do share data have better chances of having those publications cited. So in addition to love for science and the goal of achieving reproducibility in the studies, there is also benefit, practical benefit in being open and sharing the data used in analysis. And then, of course, there are growing demands from the stakeholders, funders, and publishers to make sure that the data is available, because it's more and more recognized that without the data, the studies cannot be reproduced, and the investment into those studies sometimes can be considered lost. Because we have this need to share the data, we also now have the real need to have platforms that allow us to share the data. And in this regard, I think about those as general purpose platforms that provide general features that allow you to, so to speak, park your data, make it available to others, and domain-specific data archives that focus on the imaging data or cancer imaging data. So what do we need from those generic data repositories? We want to make sure that the data that is deposited will be there a certain number of years from now, maybe when the investigator is no longer at an institution, does not have resources to maintain availability of this data. It's very critical that the data can be cited and can be persistently identified, because that gives the incentive for the owners of the data to share it, to collect the citations, and to make sure that other researchers can find it. It's also important that the repository is recognized by journals or funding agencies as appropriate for sharing the data, because it's more and more becomes unacceptable for someone to put a link to Dropbox or share data in their personal web page that is no longer recognized as a valid way to share the data. So there are several ways, several platforms that have been quite successful in providing these capabilities, and Figshare and Zenodo are perhaps the most prominent ones. And Harvard has its own platform to support data sharing. Each of those platforms has limitations. For example, how big could be that archive that you're sharing, what you need to do in order to share the data. But for the most part, these satisfy the general purpose needs of the community. But then if we talk about imaging data, this is in a way a very different beast, because we don't want to have a repository that takes everything in any format and then leaves it up to the users of the data to try to decipher and figure out how to use this data. So what one would expect from the archive that deals specifically with imaging data is certain level of curation and scientific review, so that when the data is accepted, there is at least some level of checks that this data was collected using good practices. We know what equipment was used to collect the data. We know who annotated this data. We know something about population for which this data was collected. Critical task for imaging data is the identification. And even in our days, I believe not all researchers recognize that the identification is not a straightforward task and has to be dealt using well-defined software and well-defined practices. And this goes about the metadata that we have in the images, but also sometimes annotations that are burned into the images, facial features. Sometimes there is increasing scrutiny for the identification of facial features from the stakeholders. So it's a very important topic that very often cannot be addressed by someone who has never done this before. Curation of content, that's a very important task, because when we accept a new data set into a repository, it's important to make sure that it's harmonized with other types of data. We want to be able to find the specific kinds of data. We want to know what are the fields that should be searchable and indexed in the repository. And then, of course, when we talk about imaging, we usually would like to see the images that are available from the archive to find relevant subsets of data. The repository should continuously take care of the data, because it's not impossible to identify patient information leak after the data was deposited. There should be procedures how to address this, how to remove affected data from the repository. And then also the topic of enrichment. The imaging data very often is not a static entity. Someone could have collected imaging data that contains just the images. Then someone else could come up and provide annotations of the findings in this data. Then yet another one could do the analysis using some automated tools. So the typical life cycle of the data set is one where the content is continuously growing, and the artifacts that are contributed to the data set should be possible to integrate within the repository. And the key characteristic that we need from the data to be able to achieve many of those tasks is rich and well-curated metadata. So there are many definitions of metadata, but I like the analogy that was provided by Pomeranz in here, where metadata is our map that allows us to navigate complex landscapes of data and be able to find relevant data without having to retrieve the actual data. So the library is the perfect example of successful utilization of metadata. If you go to the library, you can find books for specific topics. You can find books in a language that you can read. You can very efficiently identify where the book is, retrieve it, and used for your purpose. So imagine a library that doesn't have a catalog. It can have the most valuable books in the world, but without the catalog, this is a useless mess of paper that you cannot put to work. So that's where metadata helps us. And the repository that has been, in my opinion, the most successful repository in managing metadata and managing cancer imaging data is the Cancer Imaging Archive. TCIA has been around for probably more than 10 years. And at this point, it is the primary mechanism for sharing cancer imaging data, which is supported by NCI and has been growing over the past years, including more and more collections, both from the individual contributors and from the programs supported by the government. These slides are from Justin Kirby, who is one of the leads of the TCIA project, and they're a bit outdated. So those numbers are much more significant now. But TCIA has established procedure for reviewing submissions, integrating the submissions into the archive, curating the content of those submissions, performing the identification, and it's not limited to just radiology data or just imaging data, but it tries to curate various types of data that accompany the imaging collections. in terms of the maintenance of the archive, the analysis results submissions are as acceptable as the original data sets. So if you identified an interesting collection on TCIA and you, for example, decided to generate segmentations of the tumor, you can submit that result to TCIA. It will undergo curation, and you will have a citation and a place where this data will be available to everyone. As I mentioned, the sources of data for TCIA are both the NCI-wide initiatives, such as CPTEC and Apollo, and the clinical trial network, but also individual researchers are also eligible to submit those collections to the archive. And over the time, it definitely experienced significant growth and usage. Many of the collections, most of the collections are shared by non-restrictive licenses that allow industry to also take advantage of these collections and integrate them for developing new products. So now is the point where I want to talk about the data commons, because data commons is something that is very closely connected with the archiving the data, curating the data, achieving good quality data, but takes it qualitatively to the next level by making sure that the data that has been archived is available side by side with the storage and compute infrastructure that allows you to actually make use of this data. So while regular archive focuses on curating the data and making sure data is discoverable and can be downloaded and used by the researcher, here we want to achieve the environment where you do not need to download the data. You can identify what you need. You can very efficiently make sure that you have the appropriate tools to analyze this data, and you do not need any special resources at your site. And the definition of data commons is tightly coupled with the definition of the cloud. So it's another buzzword. And the cloud is this model of computing where instead of relying on a fixed pool of storage or compute resources, such as those that are available in most institutions as compute clusters, you have this environment where you can request exactly as much as you need. You should be able to have a good idea how much it will cost, and you can release those resources once you are done with using those. So that's the idea of the cloud and how it can enable research. So what are the advantages of using the cloud as opposed to the traditional way? So the main thing here is that we do not need to create copies of data, which is problematic for many reasons, because you, by duplicating the data, you increase the possibility of error, you introduce additional steps and overheads. You can rely, with the cloud, you can also rely on the elastic infrastructure. You can scale your network resources, storage, compute resources on demand. You do not need to spend, ideally, you do not need to spend so much time on administration and security, providing access to those resources as you do with on-premises. And also, its cloud infrastructure allows you to be more efficient in sharing your analysis results, your data, your tools with the other members of the community. So the idea of data commons definitely gained a lot of traction in NIH and NCI. And at this point, there are several initiatives that are setting up cloud-based data commons resources to implement this vision and evaluate where it can help in research. So NCI Cancer Research Data Commons is one such implementation of data commons, which is led by NCI. And the architecture of this, of CRDC, has the following components. First, there are data nodes that provide curation and cloud-based access to various types of data. So these are nodes that are specific to individual data types. Genomics data commons is the node that has been around for the longest, and proteomics and imaging data commons and canine data commons are more recent components of those data providing nodes of CRDC. In addition to the locations where data is stored, you have various supporting resources that facilitate deployment of tools, authentication, support query of the data, and ideally those are harmonized to provide uniform access to various types of data in those data nodes. And finally, there are compute resources that are integrated with the repositories of data that allow you to take the cohorts that you define for the data that you're interested in, replicate it on compute resources, and do the computation on the cloud. So here's another view of the same infrastructure in a bit more detail. So each of those data nodes provides the portal, which allows you to visually explore the data, API that can support programmatic invocation of all of those capabilities you can do via the portal, data model, and the repository of data, which is then integrated with the cloud resources that provide the computational capabilities. And Cancer Data Aggregator is this relatively new component of CRDC that is intended to provide uniform API access that would allow you to build cohorts that include matching data across different data commons within CRDC. So imaging data commons, now finally I got to the point where I talk about the imaging data commons, and the purpose of imaging data commons is to take those public curated, de-identified cancer imaging collections and integrate them within the CRDC infrastructure to support discovery of the data, search, query, and integration with the compute resources. I want to acknowledge the leadership of the team developing IDC. It's a contribution from a number of institutions, both in the US and outside. And on the NCI side, Keivan Farahani is our project lead, and Uli Wagner and Todd Peel are the leads at the Frederick National Lab. And in addition to this, we also have external internal advisory boards that provide input on the progress of IDC and advice on the direction of future development. I also want to acknowledge the technical team. There are many people who contribute to the implementation of IDC that are listed here. So the core function, of course, for IDC is to bring the data to the cloud and connect the data with the compute and storage resources. So that's our core mission. But also we want to establish the best practices for how to manage the data on the cloud, how to harmonize both the images and the analysis results. And we don't want to focus just on development of the platform, but we are actively working on use cases that utilize the tools and data we are curating to demonstrate how data commons can be of value. And here we are developing proof of concept use cases, both in radiology and pathology, and going forward in other fields. All of the components that we utilize or are developing in imaging data commons are open source. Because of this, we want to make sure that if there is something that you want to do with imaging data commons, but you cannot because, for example, your data is not public, you would be able to reproduce this under your own project, or under your own organization. And finally, as I said before, the data commons is a very new concept. We are still learning how it can be useful to the community. So what we want to make sure is we have a venue to collect feedback, to work with the users, and understand how we can develop resource that is of value. The contract to build IDC was awarded about 2 years ago. We released our pilot of IDC in October last year. The production is planned for this fall, and in the production release of IDC, we want to integrate all of the public collections of TCIA within the cloud infrastructure. We want to have basic capabilities to support digital pathology data. And in the time between the release of pilot and production release, this is the best time to provide your feedback and to kind of guide the direction of development of IDC. Imaging Data Commons is publicly available. You can browse the content without having to log in, and I will give you a demo what this means, and this is the URL of IDC. So as of now, we have a relatively small subset of TCIA, but we are on track to have all of the public collections available in the fall. It's very important to keep in mind that we cannot take any data set and put it in IDC. We are authorized to take public data sets from TCIA right now. If there are any additional sources of data, we have to work with NCI to confirm that those are allowable for us to integrate, but they definitely have to be identified. IDC hosts both the original collections and the collections of analysis results. As I will show you in the demonstration, we support various types of annotations that you can access in IDC. The front-facing part of IDC is the portal that allows you to explore what is available in IDC and build cohorts. You can visualize the images and annotations in the integrated IDC viewer. The reason we are able to support these capabilities of search and visualization, both images and annotations across collections, is because we rely on the standard to curate both the representation of data and metadata. And for this purpose, we rely on DICOM. There are many collections that can serve as examples of how DICOM can be used for harmonizing not just the images, but also various types of annotations and measurements derived from annotations. And this is a really critical key piece in implementing the IDC vision. The foundation of IDC is the Google Cloud Platform. And here we are relying on this non-public proprietary implementation, but it's one of the cloud providers that is available to the users, and we want to rely on this industry-grade capability provided by Google Cloud in implementing IDC. The reason we picked Google as opposed to other providers is our team has expertise in utilizing Google Cloud for building another resource. ISB-CGC is the Institute for Systems Biology cloud resource that has been in existence for more than 5 years now. And FireCloud is another cloud resource developed by Broad, which is also based on Google Cloud. So because of that, we had good confidence that we can migrate this technology and make IDC available in a relatively short time. Google Cloud also provides a lot of capabilities that are intrinsic to imaging. It natively supports DICOM, both as the DICOM web communication protocol, but also tools that allow to extract metadata into BigQuery tables that allow to query metadata and build cohorts. And of course, Google is well known for its ability to provision compute resources. Some of you probably heard about Colab notebooks and provides a lot of functionality which we need to support authentication and data security. Under the hood, the data is maintained in Google Cloud. So these are the locations where the DICOM files, individual DICOM files, can be accessed and retrieved into the compute nodes. And we also have the large SQL-like tables that contain all of the DICOM metadata available for query. So the idea for the workflow for the user interacting with IDC is that you would enter the portal, explore the available collections, identify subsets of data that are of interest to you, examine the quality of the data by utilizing IDC viewer, and then bring those cohorts into a component that supports computation. So Google Colab is probably the easiest component, the easiest to access. It's the hosted instance of Jupyter Notebook that runs on a virtual machine that Google gives you for free. You can create this virtual machine, have a GPU on this machine. You can retrieve the data to this machine and experiment with the cloud without having to commit your credit card. So we are developing use cases that are easily accessible, and this is one use case that we completed and are sharing right now, is the implementation of the publication by Hosni et al. Performing analysis of prognosis for lung cancer. Once you have some confidence that cloud is actually helpful to you, you can scale up your compute infrastructure. You can configure virtual machines to have the CPU, RAM, disk space, runtime environment as you need, and basically relatively smoothly transition from the Colab environment to this hosted AI notebooks environment provided by Google. So a few words about visualization. For visualizing the images, we rely on the OHF viewer. It's an open source project that was funded by NCI and gained a lot of popularity both in academic and industry projects. We rely on OHF viewer infrastructure both for radiology and pathology data visualization, and we are continuously improving the capabilities of OHF viewer and contributing back to the to this repository so that all of our functionality available in IDC is also available for anyone interested in deploying this viewer for their data. So last thing that I want to mention here in the presentation part is that IDC, as I mentioned before, is just one of the data repositories within broader CRDC, Cancer Research Data Commons. So there are already data sets that have matching data in genomics data commons, proteomics data commons, and the idea is that all of those resources will be available through the cancer data aggregator to build those matching cohorts and support cross-omics and cross-domain data exploration. So with this, I want to switch to the demonstration part. Let's see if I can resize this. Okay, so this is the Imaging Data Commons portal website that is available to you now. So you can browse the collections that are available in IDC here, and again, those are collections that are replicated from the Cancer Imaging Archive. What you can do next is switch to exploration of the content, and here you will see the exploration portal, where on the left you see the different attributes that you can use to filter the data. You can filter the data both by metadata describing the original collections, meaning CT, MR, the data that comes from imaging equipment, but also because the derived image data is curated into the harmonized format, you can also filter your cohort by the derived data. So for example, if I go to the segmentation tab, I can filter the content to include only those cases, only those patients that have segmentation of a nodule. So if I scroll down, I can see that there is one collection that has this kind of data. And I can see specific patients that match this criteria. Furthermore, for those patients that have measurements assigned, again, those are in not in any collection-specific format. Here, the volume measurement of the nodule is saved in standard way, and you can filter the cohort by the size of the tumor for a given patient. And then once you identify those cases, you can, at the level of study, you can open the study in the IDC viewer. So this will use DICOM web interface to retrieve the images to your browser. And you can see both the images and annotations in here. So you can use this interface to, for example, make sure that the quality of the data is sufficient for your purposes. It's also important to know that these URLs that you can see here can also be populated manually. So if you develop a notebook, for example, and from the notebook you want to look at the specific data set available in IDC, you can build this URL and use IDC viewer for visualization. So next, what I want to show you here, if you go to documentation of IDC, this is the place to start working with the resource. And I mentioned Colab notebooks before. So we maintain a repository of notebooks that we hope will be growing over time, implementing various use cases that are integrated with IDC. And if you click here, you can open the deep prognosis use case in Colab. You can connect to the runtime here. And you can explore this notebook on your own, but what this notebook will do is set up the environment, download the necessary packages to perform the analysis, pull the data from IDC storage buckets into the virtual machine, which is located here, and implement the use case that let me show you. Implement the use case that is described in this paper. So this is one example where the public data set, public imaging data, publicly available annotations are available in IDC, integrated with the IDC query and visualization capabilities to support the use of data commons for cancer image analysis. So another thing that I wanted to really quickly show you is how easy it is to configure a virtual machine that allows you to have tools that are familiar to you on the desktop, make them available in the cloud. So here, what I show you is the Google Cloud Platform console. It's your dashboard that gives you a window to different capabilities of Google Cloud Platform. And Compute Engine is one of the components of GCP. So what I did here, I configured a virtual machine that has a 3D slicer integrated from a Docker image. And all I needed to do to initialize this virtual machine is to specify the container image here. So I know that for those of you who didn't work with Docker, it's probably very confusing, but hopefully some of you in the audience are familiar with Docker, and you can appreciate how simple it can be to create this VM that has tools that you use. And then once I generated once I created this virtual machine and started it, I can access it through the browser. So right now you still see the browser, and the desktop that you have here corresponds to the virtual machine running on the cloud. I can use this desktop to start 3D slicer. I can pull the imaging data from the content maintained by IDC to this virtual machine. I can use any of the tools for analysis of this data available in 3D slicer. I can do annotations in 3D slicer, and all of this without having to download the data to my computer or having to install slicer on my computer. So it gives you an idea how those tools can be integrated with the cloud. So I know that it's probably quite confusing. I ran over all of those things rather quickly, but we do have documentation, and we have a number of tutorials and videos that you can use to learn more about the platform and get started with it. We also have the program where we allocate credits for the users. So you do not need to commit your credit card. You can go through the application process, describe how you would like to use IDC, and we will give you free credits so you can experiment with it and decide for your own if it can be useful to you. So I talked about this. Yeah, so that's it for my presentation. I hope that you learned why data is important in this time, and how image and data commons can be helpful. Hopefully, you got some hints about how it can be helpful to you. But of course, in order to really understand it, you will need to start using it. And I hope that we will have more conversations in the future, and you will join our community. Thank you for your attention.